All right, so welcome everyone. So just a preface. So I have been using Mathematica for what, maybe, you know, almost a year now. So I'm by no means an expert or Connor. Oh, it's all right. It's just Discord right now. But yeah, so I'm not an expert. I'm not the most knowledgeable, but I think it should be enough to get everyone started. Right. So before we get into actual the notebook, I just wanted to go over just a few things about Mathematica. So I'll just share this presentation here. Um, so hopefully everyone can see this little slideshow. If not, I'm talking about it all anyway. But so the first thing is, why are we using Mathematica? Well, it's because one, UWA pays for a license, so why not use it? Two, I think it's pretty powerful and accessible, so it's quite easy to, one, get it started, and two, get into it if you don't know any programming, stuff like that. And three, because the visualizations are good. So some of the alternatives, it's a bit hard to make plots or look at stuff like that. So yeah, this is why we're using Mathematica, or why we're pushing for it. I think it's just the most accessible. So some alternatives. So if you find that the things that Mathematica does or isn't enough for you, here are some examples, some alternatives that you might find useful. So number one is Sage. So Sage is based on Python. It's open source, and it's good for graph theory and number theory. And then obviously Python itself. So three biggest packages: NumPy, SciPy, and SymPy. So using all three of those together, maybe Matplotlib as well. Basically, couldn't do what 90% of what Mathematica can do. But again, if you don't know Python, then it's a bit hard to get into. Same thing. So Maple is essentially the same thing as Mathematica. It's just that, you know, UWA doesn't pay for it, so obviously we won't use it. And lastly is MATLAB. So MATLAB's maybe the other big one, and it's more focused towards data and kind of algorithms. So if you want to write algorithms or data analysis, then MATLAB is probably better than Mathematica, which works with more symbols, stuff like that. All right. So without out of the way, we can get started. So I will pull up Mathematica by sharing my screen. All right. And what you do is you open Mathematica, and it should look something like this. Can everyone see my screen? Not sure.
Yep, we can see it.
Cool. So this is the default what Mathematica looks like. So the main thing we are going to be looking at are notebooks. You can write packages for Mathematica as well, but I think everyone will find notebooks the most useful thing, right? So again, I have a notebook open or prepared, but just before we get into that, just because notebooks might look a little different to the one I prepared, this is what a Mathematica notebook usually looks like. So it's just white, right? But the way Mathematica is kind of structured is that Mathematica is just a front end, right? So it's just a thing you interact with, and it's the front end of the Wolfram Alpha kernel, right? So the kernel is what does the actual work. You're just feeding into here. The reason I say that is because I think the one thing that a lot of people get confused with is that their variables or functions kind of persist across the same session. So if I have something like a is equal to 5, so just setting a variable, and I open a new notebook, right? Then a is still equal to 5, even though they're two different notebooks. That's because we're running the same kernel. So just the thing to be aware of is that Variables are kind of sticky in that way. They stick around. So if you're having problems with that, just know that if you define variables, it's going to be defined everywhere for you, right? Secondly is that Mathematica is based on cells, right? So what I mean by cells is these brackets on this side. So here you have this overarching bracket and then two inside. So cells just tell you how your notebook is broken up into. So here you have an input cell and an output cell. So input is obviously where you write stuff in. Output is what Mathematica has as an output, right? You can have different types of inputs. Like in my notebook, I also have just normal text ones. But the main ones you use if you're just playing around with Mathematica is just an input and output, right? So I hope that clears up some of the kind of baseline stuff about Mathematica. Is anyone confused? Any questions so far? Cool. So now I'm gonna just open up this notebook that I've prepared, which is this one. Right. So it looks a little bit different in terms of the color, some of the things. The main reason is just because it makes text and input cells a little easier to differentiate. Just because I use some text cells to describe some of the stuff we're doing. Right. So we have a few things to get through. So if you have any questions, I'll just give everyone a breather at the end of each section, and then you can ask then in the chat or just unmute yourself if you want. All right. So the first thing we're going to look at is just navigation of a Mathematica notebook. Right. So here is an input right here. Right, there's 4 plus 1. And the way that we evaluate this cell, so if you want to get the output from an input, is we used shift plus enter. So if you hover over that cell and shift plus enter, then you'll have an output, right? So here it's pretty easy to see which one's input and output because they're different grades. So hopefully that makes it easier to differentiate the two in this notebook, right? So shift and enter is to evaluate, whereas if you just pressed shift in a cell, then it just creates a new line. So if you want to define multiple lines and then evaluate them all at once, you can just use enter and then shift enter for everything else. Right. So here I just have two different lines. So I'm assigning A to 4 plus 1, B is A plus 2, and I can even say C is equal to 3. Right. So if I press shift enter on all of these, then there's 3 lines because I've assigned 3 things, and that is the output of those 3 lines. Right. So when you're writing something in Mathematica, maybe you don't want the output. So if you don't want the output to appear every single time you evaluate it, the way Mathematica does it to suppress an output is we use a semicolon at the end. So if I didn't have a semicolon here, so don't worry about what this actually means. It's just basically finding n squared from n equals 0 to n equals 1000. But if I was to press shift and enter on this, then I get a massive list, right? So maybe you need this list, but obviously you don't want it to appear in your notebook. You can just use a semicolon, and then we can press shift enter, and then it won't be it won't show up as an output, right? So I just read a comment. Mine only has input. I might just look at your notebook. Yeah, so if you just have a normal input, then that's all it's going to have. But then when you evaluate it, so when you use shift enter, then you will have an output with it. Hope that clears things up for you here. 444Y. Right. And then maybe the most important thing, if you get anything out of this workshop, is the use of F1, right? So the reason why I think Mathematica is a little bit easier to learn is because it has its help input or inbuilt into the application, right? So for example, here I have this input here, series Bessel J, whatever, right? No idea what it does, but you can easily find out what it does. So what you do is you highlight the thing you want to know. So in this case, it's a function. But all you do is you press F1. So you might need to press function F1 or function lock F1, depending on your device. But if you press F1, then it brings up this help menu, which is maybe the most useful thing that you'll use, right? So this is the specific help menu for the Bessel J function. And all it does is it tells you how to use it, some examples, and some applications of it, right? So for example, here it says what the parameters are. So n and z are the two things you need to input. It has an example of it being used and then some of the things you can do with it, right? So here, this is what I just copied from it, but you can see how the Bessel J function can be used in that sense. So all throughout this workshop, if you don't know a function, if you want to know if there's a function, or if you want to know how to use a function, then F1 is probably the most efficient way to get to that instead of just Googling it. Right, so yeah, you can also just press F1 by itself to pull up this entire menu, and then you can search for your functions as well. Right, so if anything, if you forget everything else, just remember that F1 is a really good way to see everything that you can do with Mathematica. Right. Last thing about your notebook is how to comment. So commenting in Mathematica is you have to have a beginning and end delimiter. So just to tell you when it stops and ends. So in Mathematica, that's the bracket and asterisk. So if I write text equals 1, 4, I don't know, then it'll only evaluate this line here. It won't care about this comment here. So you can use comments however you like. Right. There's also some keyboard shortcuts. To be honest, there's not that many that you might find useful, but if you want to, you can look at some of them there, mainly to do with evaluation and the kernel, stuff like that. We'll cover a few of them in a little bit though. Right. Does anyone have any questions before we move on to the variables part? Cool. I will take that as everyone is doing fantastic. So I'm just gonna close this. Not that you need to know, but the way I'm allowed to collapse this is just because I've basically made a massive cell that has all of this. So when I collapse this cell, everything in it collapses. So that's one of the upsides of having a cell-based application. Right, so in this section are variables, so just gonna open that. So variables in Mathematica are pretty standard. So the rules for naming things, it's either a letter or it starts with a $sign. So usually people use $signs for constants. If you have some random constants you want to use throughout your notebook, you might use the $sign first, but you can use that however you like. But one thing I will say is that it's not a hard and fast rule, but I would say don't really start your variables with uppercase letters, just because a lot of the inbuilt functions have uppercase. That's how they're defined. So I would stray away from that just in case you have some conflicts. So yeah, a common thing that people use to name their variables is camel case, so just lowercase, and then everything else is uppercase when you start a new word. Right. So the way we assign variables, just how you think, is using the equal sign. So we set whatever our variable is. So our variable can call anything. So let's say my variable equals, and it can be anything. So let's say x plus c, right? So even though x isn't defined, we can set a variable to have another variable in it. That's okay. So when we run this, there is 3 lines because we have 3 assignments. So c, my variable, and then we're looking at c again. So like I kind of prefaced with, I think a lot of beginners kind of get confused with how quote unquote sticky variables are. So if you define a variable once, then it'll always be defined until you clear it, right? So what I mean by that is if you have this c plus 5 in every other cell, that c is still going to be 5, right? There's a few ways you can clear it. Probably the easiest way is to use the clear function. So if you want to clear a variable, then you can just write clear and then in brackets whatever your variable is. So for example, here we set c is equal to 5, so in our output, c is 5, right? But after we clear it, c no longer is assigned 5 because we've cleared that variable and now it's just c. Right. And then if you want to clear every single variable in your kernel, then we use this command, which is clear and then global asterisk or global apostrophe asterisk, which basically just means in your global workspace. All right. Not sure why it's an apostrophe, something to do with how the global environment is defined, but don't really worry about it. You can just use that without worrying. All right. So another useful thing if you want to write variables is if you want symbols. So if you want these lambdas, these etas, these xi's, then what we use is the escape key. So if you just press your escape key, then you get these 3 dots. So that's the alias delimiter, basically just says this is a different form of input where we can get symbols. So once you have your alias delimiter open, then you can start typing whatever your variable is. So let's say I want an omega, right? I can omega. I can type in omega, and then when I press escape again, I'll have an omega, right? And there's basically every Greek letter, I assume here, or there's pretty much everything, yeah. Everything you will need at least. Personally, I don't use them. I just write out the symbol as the variable, just because I'm too lazy to write escape. But you can use this if you want to make them a little prettier, stuff like that, right? But these work the exact same as normal variables. They're just not alphanumeric. Right. And then the last thing I want to note about variables is that if you want to see every single variable that you currently have defined, then this is a good command just to see what you've used before, if you need to clear anything, or just to make sure you don't name things the same thing, is just this names command. So here, this is every single variable I've listed so far, so I know that if I wanted to find something else, probably shouldn't use any of these. Right. Any questions so far?
Could you repeat the last part I missed?
Yeah, sure. So this last part about names. So this will give you a list of every variable that is currently defined in your kernel, right? So if you've assigned any value to any of these, then it'll show up here. All right. Cool. Before we move on, I'll just say one last thing. Another way to obviously clear everything in your kernel is to restart your kernel, right? So if you want to get rid of everything, I don't know, maybe you like give something up and you want to start from a fresh slate, you can go to evaluation and quit kernel, right? So what that will do is it'll restart your kernel, so it'll be wiped blank. So it's more useful if you have packages, stuff like that installed, but it's another way if you don't want to clear global, or if you just want to make sure that nothing is defined at all, right? But yeah, just something to note, right? In that case, I think we can move on to the arithmetic in Mathematica. Yes. Oh yeah, okay. So it is a backtick and not an apostrophe. I think I said apostrophe by mistake. But yeah, backtick is the one under escape, and it's I think above it also a tilde. To be honest, I never actually write it. I just copy paste it. But if you want to write it, then there you go. Thank you, Nick. Right. So arithmetic in Mathematica, again, it's pretty much how you expect it to work. So with any variable or number, you can use the standard plus, minus, times, divide, and exponentiation. If you want to write parentheses, then you use either round brackets or curly brackets. We don't use square brackets. The reason being is that square brackets are used only for functions, stuff like that, right? So only round and curly brackets if you want to define order of operations, right? So for example, if I have a plus b, right, I can have times c to the power of d, right? And when I evaluate that, then it'll do exactly as you think it would, right? And you can use brackets however you'd like. On the same note of having kind of those ways to implement symbols, stuff like that, you can also kind of have a display kind of style for powers and fractions and radicals. So the main way you do that is using control. So if you want a fraction, right, which is normally the slash key, if you write control and slash, then you get a display style of how to do that. Use that however you like. It can get a little messy if you have too many of them used at once, just because the text gets smaller, but where it's appropriate, it's fine. I know a lot of people don't like using it just because if you're writing your Mathematica notebook in, say, a text file, then it becomes harder to put that into a Mathematica notebook. But obviously, if you're just writing in a notebook by itself, then it should be fine, right? So that's the same thing for powers as well. So if you just use control and then 6, which for me is the key for a caret, or the thing that makes your superscript, then it'll give you a superscript, right? And same thing for subscript, which is control, and then the minus, which is the key used for the subscript button. And you can get a subscript if you want to name some variables, stuff like that. Cool. And then same thing for radicals. So for radicals, it's 2, I guess, because it's like the square root. But if you press Control and 2, then you get a radical. Right. And that's it for that. One other thing, just because it comes up frequently enough that it's useful enough, I guess, is that if you have a space between variables, then it will default as multiplication, right? So here, a space b, that will default to a times b, so that will be 15, right? And lastly, in Mathematica, substitution. So if you want to substitute one variable for a value, right? The way it works is you have this slash dot rule, right? And that basically says, hey, I want to substitute everything on the left of this, and the things on the right is the rule. So here I have an expression in terms of E and F, and here I'm saying that I want to replace some values in the expression, so I use slash and dot, right? And then on the right hand side, I will put in whatever I want to change, right? In this case, if I wanted to change e to 4, then all I do is, well, e and the keys dash and then the right angle bracket. So this arrow sign, and then when you space it automatically converts to that arrow, right? So I want e to go to 3 to 4, let's say to 3, right? This basically just says expression, but I replace e with 3. Yep. And you can do the same thing for multiple. So in this case, if you treat this entire line as an expression, then you can also do this with f. So I can do this expression, but e is replaced with f, and then this expression, but this f is replaced with 4, right? Can get messy if you have quite a lot of them, so you can also use bracket notation. So encapsulate everything you want to replace, and then just type in everything you want to replace it with, right? So in both cases, these both end up with 25, but they do the exact same thing. It's just that this one might be a bit cleaner if you have a lot of things to substitute at once. Cool. All right. Do we have any questions so far? What if the root is 1 over 1/3? So I think, yeah, control 2 only works for square roots because I think square roots are is the most common one. So yeah, I don't think there's a way to make custom roots. So I think just sticking with to the power of 1 over 3 is probably the main way you would do it. So hopefully that answers that. Cool. Okay. So the next thing, which I think is one of the more useful ones, is functions, right? So functions are basically just variables, except you have specific parameters you can put into it, right? So yeah, functions you can think of the exact same as variables, except there's some variables that we want to put in place in our function, right? So the notation for a function is that we have whatever our function is called. In this case, I've just called it f, but we have in square brackets just to say that it is a function. And then inside those square brackets is whatever our variable is. So note that we have an underscore after this variable, and that just tells us that everything in this left-hand side, if it has an x, then that is what we're going to be looking at as what is our function have in terms of parameters, right? So I could also have y as well, and then I would have a y over here, if anything, right? The one thing that's different about functions from variables is just that we usually use set to lay, so rather than just set. So we use a colon before the equals. And what that does, it's a bit complicated, but in essence, it just means that we store our function to be this expression, but it won't evaluate it right away, right? So the reason that might be useful is this example of g of x, right? Or g of x and some other parameter. So it has x as one of the inputs, and the other one is this upper bound, right? So in short, this function on the right-hand side, it just gives me the series expansion, this series power expansion of some function of x, and I want it to, let's say, 10 terms, 11 terms, whatever this upper bound is, right? So in this case, I'm kind of parameterizing the upper bound. So maybe I want it to 10, to 20, to 100, whatever. So in this case, I will turn it into a function and have this as one of the inputs, right? If we don't have this set delay inside it, then when I try to evaluate this, Mathematica will be like, what does this mean? Because I just have upper bound as a parameter in this function, right? And the function of table, it needs a number for this. So obviously when you have g and you want to find to 10, it'll have a 10 in this instead of just this function variable upper bound, right? But if we just use the normal set, then Mathematica will get kind of confused because we're just saying, hey, this is what I want you to do, but I'm not actually giving you any numbers. So then it gets a bit confused, doesn't know what to do with it, right? So if we just use set delay, then it'll say, okay, this is what you want, but I'm not going to try evaluate it, right? So that's one way it can be useful. But there's also some problems with if you assign the same function to the same variables. But if you just use set delay, then you don't have to worry about it. Right. So if I evaluate this now, then that's okay. Nothing shows up in our output because I've used set delay. So it isn't actually evaluating it. It's just storing it as its definition, right? So now if I say I want g of x to 10 terms, I can shift enter and I can get whatever that expansion is, right? And even more so, I can get g of 2 in terms of 10 terms, and I'll get that number, right? So then you can easily define functions in terms of a lot of different parameters. Some parameters where you don't necessarily need to have the value of it right away, right? So that's how you define your own functions. I think that'll suffice for 90% of the functions you need to make in Mathematica. But also Mathematica has a ton of built-in functions. So basically anything you want Mathematica to do, it probably has that function. You can either just look it up or just, if you are really desperate, look it up on Google and probably someone has the answer or a workaround to it, right? So functions in Mathematica are the exact same. So it's just uppercase, and then it has your square brackets, and then whatever the parameters are inside. So in this case for sine, if you don't know what it does, we can just use F1 on it. It'll tell you exactly how to use it. It says here it's in radians, and then also how to use it in degrees. And the cool thing about this is you can just copy paste it, or you can just run it in here as well, because this is actually a notebook as well. But you can copy it, put it into your own notebook, see if it works, play with it, and then get something out of it. All right. But yeah, same thing with this table. If you don't know how to use it, you can just press F1. It'll tell you the different ways you can use it and the parameters you need. But essentially, table is just a more functional way of making a for loop, right? So in this case, it's saying that my rule is I squared, and I want it for I to 1 to 10, all right? So in this case, I should get all the squares from 1 to 10, and that's exactly what it is, right? Lastly, with functions, one useful thing you can use for functions is if you're lazy to wrap your function around. So you do need to close the open and close brackets if you're using the brackets, of course. But if you're lazy, or if you have multiple functions kind of nested in each other, then you can use the at symbol instead. So what I mean is if I do sine at pi over 2, actually I need pi over 2 like this, right? Then it's the same thing as writing sine of bracket pi over 2 bracket. You just don't have to close the bracket up, right? But then you can also encapsulate with another sine, right? So you get sine of 1, whatever that is. But in this case, you don't have to close all of your brackets if you have multiple functions nested in each other. So as you learn more functions, you might find useful ways to use at. Just be careful when you use it, because some functions need more than one parameter, so it could get a little messy using the at notation. But as you use your functions, you can see like typical functions that are good to use at for. Right. Cool. Anyone have questions about using functions so far? All right, I will take that as me doing a good job, or people not listening, but I hope the former. So our next thing is about lists. So I think lists and arrays will be the last thing I'll talk about, and then I'll give everyone a quick break if they want to look at some of the examples or just play around with it, right? So lists and vectors are treated as the same thing, right? So I'll just call everything a vector from now on, sort of like how R kind of handles its data structures. But a curly bracket will denote a vector, right? So a curly bracket and it's separated by commas. So in this case, v1 will make a vector with 3 elements, 1, 2, and 3. And this is the pretty standard way to define a vector, right? If you notice before, table also generates a vector. Same thing with series, I think. But most things, if it's going to be generated as a list, it's the exact same way. It's going to be just in brackets, right? So, like you might expect, Mathematica has a ton of functions for vectors specifically, right? So you could have the cross product, dot product, or vector angle. In fact, if you just search up vector operations in your F1 menu, there's an entire list of everything you can do with vectors, and even more, I think, but these are the most common ones, right? So if you want to look up something that, probably exists or is common enough, then it's probably in Mathematica. You just have to know what the name of that function is, right? So each of these behaves exactly as you think. If I define v1 and v2 as follows, then each of these will have some value. You can check if that's right, but you'd hope it's right. Cool. So that's how you denote a vector, and I guess it's not really a functionality, it's more of a corollary, but the way you also define multivariable functions is as a vector. So whether you think of them as vectors or not, that's how the most common way to define a multivariable function. So in this case, I'll have some vector field or some multivariable function, and I'm just going to turn it into a vector where the x coordinate is sine of x, the y coordinate is y of x, and the z coordinate is z. But it doesn't need to just be x, y, and z. It can be across, obviously, right? So this is a vector, so we can do things that you can do to vectors, like get the gradient vector of that. So that's the same as just finding the derivative of each of these with respect to x, y, and z. So here we have a vector of vectors. So the first vector, if you remember what the gradient function does, this is the derivative with respect to x, with respect to y, and with respect to z, right? But yeah, gradient, exactly how you expect it to work, and these are the derivatives you're taking it with respect to. But again, if you want to know how the gradient vector works, you can just press F1, see how it works, right? Okay, so you might notice that this is also a vector of vectors, and as you might expect, this is just a matrix, right? Matrices are just vectors of vectors. So in this case, for example, I have m1 to be whatever the vector 1 was before, and then these other vectors here. So these don't actually have to be the same length. It's just in that case, it'll be an array instead of a matrix. But for most cases, you'll usually have vectors of the same length. So I'm just going to call them matrices from now on. All right. So matrices, just like vectors, you have a ton of functions built in for them. So determinant, inverse, and eigenvectors, eigenvalues are the most common ones you're going to use for matrices. And just because it's common enough, like basically in everywhere to use to get the eigenvalues or something. You can use eigensystem to get eigenvalues and eigenvectors that are paired. What I mean by that is if you just find the eigenvalues of this matrix and the eigenvectors of this matrix, which I need to define this matrix first. And I'll just comment these out for now. So if you find the eigenvalues of this matrix, if you don't know what an eigenvalue is, it's just some property of this matrix, right? But here we have 10, 10, and 1 as the eigenvalues, and the corresponding eigenvectors are here. The only problem with that is sometimes the eigenvalues and eigenvectors might not match up directly. So this eigenvalue of 10 might necessarily not be the same eigenvector here. This one might not pair to this one, right? So you can just use eigensystem, which will give both eigenvalues and eigenvectors, and it'll make sure that they are paired. So if instead I use eigensystem, right, then the first one we get is your eigenvalues, right? So in this case, 10, 10, and 1. And the second one is all of your eigenvectors. So in this case, it is the exact same as before, but now you know that this eigenvalue of 10 corresponds to this eigenvector here, this 10 and this eigenvector, this 1 and this eigenvector, right? So just a useful thing, because I think a lot of people will find that useful because you use eigenvalues everywhere, right? And another thing about matrices, so you can have them as vectors of vectors, but you can also look at them as a display form. So the way you use that is matrix form. So it's a function. So you can use your square brackets or you can use your evaluate at. Or there's another way that a lot of people like to use, which is like this, right? Just 3 ways to do the exact same thing. There's just 3 ways because people find a few of them easier to use than others, right? But basically it'll just turn into a display mode of what that matrix is. So if you're looking at matrices, it's probably easier than looking at a vector of vectors. So it's a way you can turn that form into a more readable form, right? And you can also construct vectors using this display mode. So if you have a starting input, right? So this entry here, you can use Control Enter and Control Comma to add rows and columns, right? So let's say if I write Control Enter, then it'll introduce another row. So if I just make this B, right? Then now M is a matrix with the first vector being A, which in this case is 5, and the second row being 3, which is B, right? And I can also introduce new columns by using Control and comma, right? So that will make this a 2 by 2 matrix. And again, if I just type in some values, that just defaults to the vector of vector, right? So an easy way to go from one or the other, or if you don't want to write your matrix in this form, you can input it like this and it'll automatically turn into this form here. Okay, so that is where we're gonna take a break. Does anyone have any questions before we take a quick break? Okay, so if you look at the examples that I've put in the other voice or text chat, here are a few examples, some things you can play around with. A few of them are using calculus, which we haven't done yet, but you can probably figure out if you are bored. But there's a few questions on matrices and some of these functions and how to use them, right? So take a look through it if you want. But I'll just take a quick break and we can get started again at, do you have something to say, Nick? Yes, I would agree. Much better than your class pad. Probably going to use it the same way, but it feels a lot better to use, to be honest. But anyway, so we can come back at maybe 3 o'clock, finish this out, and then last 45, 30 minutes can be for questions if anyone has any, right? So we'll be back in 10, 12 minutes. Feel free to ask any questions by then if you'd like. Okay, if anyone has questions, maybe ask Nick. I will be back in 3 minutes. So I don't want to call anyone out or put anyone on the spot. But a general comment. I hope this is helpful so far. If anyone has any feedback or any thoughts about, how useful this was to you or anything that you'd like to see, if you want to put in the chat or just DM either me or Nick, that would be greatly appreciated. Okay, thank you for that. I'm glad, yeah. I think the main thing is that there's just so much stuff you can do with Mathematica, especially because it's like a professional grade um, engine. But yeah, it's actually just like for most uni students, the things you use it for, like just like calculating derivatives or plotting stuff, it's actually just like really fast and easy to implement. Um, but yeah, I do agree. It looked very intimidating at first. Um, Yeah, I think one of the important things that you can do is just, I mean, this is applicable to like any quote unquote programming language you use, is just like looking up how to do stuff. Because obviously there's Stack Overflow that will help you with everything. Um, yeah. Also to note that I don't think this workshop will really scratch the surface on what Mathematica can do. Um, because I don't think any of us are going to use it for like creating our own packages or like doing some real in-depth analysis of anything. But if anyone is interested in that, um, I mean, I for one would like to learn just making like a lot more intricate plots, making more functions in terms of like sophisticated pure function stuff like that. Um, but yeah, anyway. Yeah, fair enough. We like that's you know that's those are the two things that we haven't covered yet. But rest assured, it is coming up. I promise. Um, well, maybe before we wait a bit, if anyone wants to see some cool stuff I have done, I don't know. Just see the kind of stuff you can do. Um, what have I done? So, for example, this is my assignment I did for Math 3022, which is scientific and industrial modeling. This was before I knew how to do a lot of it, but um, you can just like basically make an entire worksheet with whatever you're doing kind of embedded with it. So like you can break it up into questions, make your plots, and then evaluate all of these terms, differential equations, stuff like that. And I don't know, it just looks nice to me, to be honest. But yeah, just an example of some stuff you can do, you know, a lot of numerical analysis. I think Mathematica is really good in terms of its numerical integration and solving. Um, but yeah, cool. Okay, yeah. So I can go over that, yeah. So that is one thing I kind of mentioned that you could make titles and format it. So maybe before we get into the next section, I'll just say a little bit on how to do that. So actually, why don't we start now? Because it's basically 3 o'clock anyway. So here I have like a title, main title, and then I have text and then inputs, right? So I'll just create a new document just because this is what it usually looks like. But you can do all of this in format and style, right? So there's shortcuts for these. So I'll use Alt 1, Alt 4, Alt 7, and Alt 9. Those are the usual ones I use. So basically, when you start writing normally, right, this will be a normal input cell. So it behaves exactly as you think. It goes input output. So if you want something to be anything besides an input cell, then you can format it and pick a different style. So right now it's input, but you can have code, all of this stuff. In fact, there's like a lot of stuff you can do. Like I think there's even stuff for like theorems, corollary, conjecture, stuff like that. Just because some people apparently write like notes and stuff in Mathematica. But besides the point, so for example, if I wanted to write a title, I can press Alt 1 and this will be a title, right? I think the one thing to note is that just be aware of what cell you're currently in, right? So here, if I press enter, I'm still in the same cell, right? You just see that it's gotten bigger. So if I say Alt 7 and I have like some subtitle or Alt 7 subtitle, this is in the same cell, right? Which is different to if you have a new cell, go Alt 7 and write a subtitle, right? I'm not really sure why Mathematica does that or like what is, there's a few subtleties because obviously the like tabbing has changed, the text, whatever. But just as a rule of thumb, if you have different text types, so whether that's a title, a subtitle, text, or input, then probably separate them into different cells, unless this is the look you're going for. So if you want to start a new cell, just make sure you have this kind of divider and this plus, and then it will say like, you know, what input you have. So if you can go to style like this and then choose one of these or one of these, which are like random things that there's a ton of them. I don't know why. But yeah. And then the other thing to say is about style sheets. So the way I was able to get my worksheet to look like this, and the reason I wanted to is because it has these like boxes around the inputs and stuff, is to go to format and style sheet, and there's a bunch of different ones. So the default one looks like this. You can reverse the colors to have the black background. Articles, books, I don't know, like this stuff. The one I used was standard report. So it just gives these outlines so it's easier to differentiate. So it's useful if you're typing a lot of text. But yeah, you can play around with these. You can like format your own if you want, change all the types, whatever, all of this stuff, text alignment, I don't know. A lot to play with, but honestly, I just like just choose one of these and you are probably fine. But yeah, that's basically as far as I go with customizing a notebook, just because I think that's basically all you need to do. But yeah, go ham if you want to do that. All right. So that being said, let's move on to I think what most people are going to use Mathematica for. So that is, you know, standard calculus and plotting, right? So obviously these things before, you need to know them, but this is really what everyone's going to use it for. So calculus, right? Differentiation, probably the most useful thing you'll use it for. And Mathematica knows that. So instead of having to write differentiate or diff, it's just d. The function is d in Mathematica. So the way it's done is you have d, your function, and then what you're differentiating with respect to, right? So this first line is going to differentiate this function x to the 11 with respect to x, right? If you want to differentiate it with respect to more terms, so let's say you want to differentiate it 10 times with respect to x, you can put it in brackets like this. Or alternatively, you could just write out x 10 times like this, right? I think that's 10 times. That is too many times. That's 11, right? But yeah, it's a bit shorter that way. But yeah, you can do that with as many variables as you need. So if you have x's and y's as well, right? So this here will be the derivative of this function with respect to x and then with respect to y. And then we can also check, for example, that clear-outs theorem holds. I think clear-outs, yeah. And then they're the same, right? So it's as easy as that, right? Same thing with integrate. So instead of d though, we have to write out integrate, unfortunately. But it's integrate function thing you're integrating with respect to, right? And then if you want a definite integral, you can put in the lower bounds and upper bounds in curly brackets, right? And then you can also nest multiple integrals. So if you want to do multivariable integrals, you can do that as well, right? So yeah, it works exactly as you'd imagine, right? And then the last operation you'll probably use is dsolve, right? So there's actually a function called solve in Mathematica, just solve without the d in front, which is just for solving normal equations, obviously. And dsolve is specifically for differential equations, right? So the way that dsolve works, right? You have whatever your ODE is, right? So in this case, I have it to be this differential equation here, and I'm setting it to 0. So note the fact that we're using a equals equals, right? So like in Python, this is basically saying I'm not assigning it to the value 0. I'm just comparing it to 0 and seeing what the values of y must be if it has to be 0, right? If you set it to 0, then it will get a bit funky because then you're saying, well, this has to be 0 and there's nothing else it can be. So just saying it's 0, so with this equals equals is what you have to do, right? And I've just written it out here, but obviously you don't need to do this. You can just copy paste it right into here. Just if it's really long or if you want to use it more than once, that's why I've turned it into a variable. Because again, variables can basically be anything you want it to be, right? So I've also used this prime notation. The reason being is because we want to know what the independent and dependent variable is. So I'm just using this form. So instead of having to write d and then y x x, it's a bit shorter this way. So I'm just saying y is a function of x and you're differentiating it twice. So comma notation does work when you're writing these differential equations. Yep. And then when we're solving it, we just give it the dependent variable and the independent variable, so y and x, right? So if we just go ahead with this, it'll give us what y of x is, and then this is the solution, right? So C1 and C2, these are just constants, right? So if you have initial conditions per se, then you can get rid of these. So the way that we include initial conditions, you just treat them like other equations that you're trying to solve, right? So instead of just having the one equation we're solving, which is wanting the differential equation to be 0, we also have initial conditions of y of 0 must be equals to 2, and y of 1 must be equals to 1, right? So we wrap all of these in curly brackets, just so Mathematica knows that these are all equations. Actually, there should be 3 here. But Mathematica knows that these are the equations that govern our differential equation, right? And then same business as usual with the y of x and x at the bottom. So here, if we solve this, there's no constants. It's just instead of all of the stuff we had before, now we have cotangent and cosec as our constants, and there's 2 up front, right? So it can solve these constants for you if you don't want to do it manually as well. One thing I forgot to mention also is about indexing. So if you have a vector, so let's say my vectors or list, right? Whatever you want to call it, and I have 4 things inside it. The way you access a vector is not with one bracket, because a single square bracket is used for functions, right? So the way that you index is actually using 2 brackets instead of 1. So this will return the first value in that list, right? So it does start indexing at 1, if that makes you cringe or not, but that's how it is. And same thing for matrices as well. So you can also, if you have a matrix, you can also stack these indexes to get an entry of your matrix. All right. So next up is about numerical solutions. So quote unquote in the real world, unquote, whatever. Most integrals are not closed, right? So you need to have a numerical way to integrate them rather than just a symbolic analytical version. And that's one of the main things that Mathematica is known for. In fact, I think they're, nsolve and or at least their numerical integration is pretty good. But it can also just be used for any integral that you want a decimal number for, right? So it works the exact same as integrate, it just has an n in front, right? So if we just have our integral here, which is x cubed plus x minus 1 over x from x 1 to 2, right? When we evaluate this, we just get the exact value, 21 over 4 minus log 2 of 2, right? So if you want that as a decimal, there's 2 ways you can do it. So firstly, you can actually just replace this integrate with n integrate, and that'll always give you a decimal when you can, right? The second way is to use the n function. So this n is like numeric, or I don't know, like just gives you a number, right? So you can stick anything inside here and it will evaluate it to some decimal points, right? You don't have to specify it, but you can specify how many decimal points if you just put it next to it. And that'll, or not decimal points, sorry, significant figures. And that'll give you the actual number that this example integral is, right? And like I said, you can use that for n integrate as well. So for example, if I wanted to find the integral of the exponential integral, which doesn't have an elementary closed form, right? Let's say from x from 2 to 3, I can do that just fine, right? Whereas integrating this by itself, you have the exponential integral at -3 and exponential integral at -2. Doesn't really help. So n integrate, it gives you the exact numbers for integrals, whether they're closed or not. Just gives you the decimal, right? And you can use just the normal n as well. So this also works for nsolve and ndsolve if you just want approximate answers, or if you can't find the exact solutions as well. All right. In terms of simplification, it just works how you think it can. So there's simplify, expand, factor, full simplify, I don't really know what the difference between full simplify and simplify is. I just know that you can just spam simplify and it'll usually work out, right? So for example, if you want to combine fractions together, you can just use simplify and it'll simplify that fraction for you. Works with powers and brackets, stuff like that as well, right? So if you just spam simplify and expand, it'll usually work out like 99% of the time what you want it to do. But yeah, there's a bunch of other ones that I've written here. So if you want to play around with them, if you want to use them, because whatever your use case is for, just look them up using F1, see how to use them, see if you find them useful. And yeah. So any questions before we get onto how to plot stuff? Cool. So I think this is what everyone wants to use Mathematica for. So plotting is very easy. And all of the different plots you can make, they basically have the same structure, right? So the main function that you'll use is the plot function. So plot and in like stream plot, plot 3D, parametric plot, all of those, they have the same structure of input, right? So you have whatever your function is and then the square brackets. And then firstly is your function, or in some case functions, that you want to plot, and the ranges for that function, right? So here I've just defined a few functions, and then just like I said, it's the function. So in this case, I'm plotting this function here. And the range is from x goes from 1 to 2, right? So if I just evaluate this, there you go. It's the plot, right? Pretty standard. Nothing special. So in terms of how you can customize your plot, the way that Mathematica does all this is you just add it as a parameter. So if you just put a comma, and I'm just going to put a new line just to look at this stuff, there's a ton of different things you can do. So firstly, if you want to rescale it, so let's say you want it to be the y goes from 0 to 6 instead, then we can use something called plot range, right? So if you start typing plot, it'll have like all of the things you can do. So plot range, plot style, plot label, that's the main three that everyone uses. But plot range, I'll just click tab to autocomplete. But it just gives me this arrow, which is the same as this arrow using the hyphen angle bracket. And then we can give it its plot range, right? So this is given as a vector. So let's say I wanted to go from 0 to 5. I can just do that, right? And I will go from 0 to 5 instead. Right. The other thing you can do is plot style, right? So plot style is the style of the line, basically. So here's a few options. But for example, you can make it green. You can make it red. I'm not sure if you can use hex colors. I'm definite that there's a way to do that. I'm not sure if you can put them in by default though. Maybe you can. I'm not sure if that's actually working though. But there is definitely a way, I just haven't been bothered to look at it, right? And you can also make it thicker, make it thinner, make it dashed, stuff like that, right? So right now I'm just going to leave it as green. And the other thing that people like to do is plot label. So I can make it automatic, so it'll automatically label my plot for me, but I can give it a title, whatever you want to call it, right? And maybe one more thing is plot legends, or if I can spell it right. So plot legends will give you kind of a key of what your plot is. So this is more useful if you have more than one plot. But again, I can give it plot name here, right? And it'll have the plot name. So if you have more than one plot, you can give each of them a name, right? So we'll get more onto that. But for now, just a few other plots you can use. So one is stream plot. So stream plot will give you pretty much a vector plot, but it'll plot a vector field, and it will have the flow or direction that that field goes in. So for example, I have two functions here, x squared and x squared plus y. So if I turn that into a vector field, so now this is a vector where the x coordinate is the function 3 and the y coordinate is function 2. All right. This plot will basically say this here is the derivative or the direction at that specific point, right? So this here is our function per se, which in this case is a vector. And then afterwards we have our ranges. So in this case, I'm plotting from -2 to 2 and -2 to 2 for x and y, right? So this will give me the vector plot of this function. So you can see kind of the way that it evolves. So if you start from here, for example, you can see what happens. So if obviously you're doing math 3021, pretty useful considering it makes everything you do by hand trivial, since you can do this in like 3 seconds. But it's also useful if you just want to see what the vector field looks like, right? And this is the same as vector plot. So instead of stream, if I write vector plot, right? Vector plot does the same thing, except it's just arrows. But I find it's less useful because it doesn't really show the qualitative behavior of what it looks like, especially near the critical points, right? But yeah, I think stream plot is quite useful. And then the last kind of plot, I guess one of the last kind of plots is parametric plot. So if you have, let's say, a vector defined function, you can plot that parametrically. So let's say I have this parametric function here in 2 dimensions and it's based on this parameter t. I can use parametric plot. So here is my function and then here is my range. So in this case, I'm plotting from t goes from 0 to 2 pi. And we can see exactly this is a parametric plot, right? So if you plug in t is equal to 0, that starts at 1, 0. So you can see that it starts here, and then as t evolves, it goes around and up here, right? So easy way, so you don't have to turn it into Cartesian equations like elimination, all of that stuff, right? So all of these things, there's also 3D equivalents. So if you want to plot something in 3D rather than 2D, it's the exact same, right? So I can also do parametric plot 3D, and it works the exact same way, except your input will be in 3 dimensions instead. So let's say instead of just this, I add a new coordinate for the z direction, and let's call this just t. I don't know, let's play around with it. And I can make t go from 0 to 2 pi, right? So might take a little bit, but here is our parametric plot, right? So it does the same thing except it increases in the y direction. And I'll just decrease the size of this a bit. But you can kind of see it looks the exact same as the 2D version, except it evolves over the z direction over time, right? And yeah, you can kind of move it around, resize it, play with it like that. But you can do the same thing for just normal plot. So plot 3D works the exact same way. So let's say I have a multivariable function. So let's say x squared plus y squared plus c. And I'll make it go from -2 to 2. Y goes from -2 to 2, right? And maybe instead of a constant, actually define it, right? So now I have this function, right? Very cool. So yeah, that I think I'm not sure if stream plot has a 3D equivalent because that gets pretty messy, but I think vector plot, yeah, vector plot 3D does exist. but I think the usefulness of 3D vector plots kind of fades, right? So that's the basics on how to plot, right? And some of the things you can use. But yeah, you can change a lot of the parameters for plot. So if I just go to F1 on plot, here's the documentation. But if you go into details and options, it'll give you like every single parameter you can change, right? So there's a ton of stuff. I haven't touched like half of these. But if you want some specific use case, want to make some really nice plots, this could be a way to do it. Okay. One useful thing that I'd say is combining more than one plot. So there's multiple ways you can do it. So the first way you can do it is just how you plot something. So if I have in square bracket or in curly brackets, sorry, my functions. So in this case, I will graph function 1 and function 2, right? So function 1, function 2. So I'm plotting both of those now. So I've just told Mathematica, these are my functions in this vector here. And let's go from -2 to 2, right? Then it will plot both of them automatically, gives them different colors, right? But you can also change the colors itself. So let's say I want the first one to be green, the first one to be blue, and then you can do that, right? The second way you can do it is using the show function. So if you have a ton of different plots, you can use show. So basically what you can do is you can basically turn your plots into variables, right? So in this case, I'm setting P1 to be this plot, right? So again, like I said, variables can be anything you want. So if I call P1, it's this plot specifically, right? And then same thing for P2, but I can give it a specific plot style, plot legend, whatever you want. And the thing you can do is you can combine them together using show. And here I've just said, I want to show P1 and P2 together, right? And the neat thing about this is that you can kind of make a general plot and then kind of refine it and then only include some things you want. So for example, I've made this P1 and P2, but let's say I don't want the entire plot. I only want it from y is from 0 to 6. I can just change that when I'm using show. So now when I show it, it's only from 0 to 6. And I still have my original P1 the exact same if I still want to use that later. All right. So if you treat plots as kind of objects or as variables, then you can kind of get more mileage instead of having to create a ton of different plots with different, plot styles or plot ranges, stuff like that. All right. Cool. So that should be like, a decent chunk of what everyone's going to use plots for in Mathematica. But the last thing I want to talk about, just to round this off, is some more advanced ways you can plot stuff. So that's with manipulate and animate. So right now we're just dealing with static plots, they don't change. But you can make your plot interactive with a slider using manipulate. So essentially, if you want to see how a parameter changes your function, then you can use manipulate to do so. So the way manipulate works is you just put something inside it that will be dependent on a parameter, right? So in this case, this plot 3D is dependent on this variable a, right? So if I try to run this and I comment out everything else, if I try to run this plot 3D so far, because a is currently defined, if I don't have anything defined for a, it's not going to plot it, right? Because it's trying to plot this function, but it doesn't know what a is. So in that case, we can just go through, a is equal to 1, a is equal to 2, a is equal to 3. You can kind of see what's happening. But you can also use manipulate to kind of step through that. So I've put in that here as the input, and the second input is the range for A. So in this case, I want A to go from -2 to 2. So when I do this, it will give me a slider for A. And if you press this plus icon, you can see what the value of A is. But then I can slide through it, right? So that's kind of what it looks like. And you can see what A does to it as you move the slider back and forth, right? And you can also automatically go through and animate it, right? So this animation is exactly what animate does. So in that case, animate is kind of obsolete. But one thing that kind of irks me is that when you do this, the mesh gradient kind of disappears just because it's trying to render it on the spot as you're moving it. So the animations don't really look good because it just kind of looks like a blob that kind of gets quantized a little. So for 2D cases, it's pretty good. So let's say if I wanted to manipulate, let's say sine of A of x from x goes from 0 to 10. And let's say A goes from 0 to 2, right? So if I look at a 2D version instead, it works pretty fine just because 2D is a lot easier to render. But yeah, for 3D plots, it can get a little slow, right? So the reason is because it's trying to render each frame as you do it. So obviously the way to get around that is to cache all of your plots, right? So I understand that I don't know, or I don't think a lot of people will care about this too much, but if you want to make cool animations, this is what you have to do. So you cache all of your slides. So in this case, you do the same thing, except you evaluate your plot at each of the values of A or T that you want. So the example I'm using is this function here. So this is just like a concentrated mass that's moving over time, right? And it also diffuses over time. So what I can do is I can take this plot here, and this is parameterized with t. So if I just try to run this by itself, it's not going to know what to do because I don't have t defined. But if I make a table of this, so a table will just make a list with whatever our expression is here and evaluate it at some value of t. So in this case, I have t going from 0.05 to 3. And if you add the extra step size, it's in steps of 0.01, right? So there's going to be, you know, like 250 frames of this. So don't run this if, you know, your computer's, I don't know, struggling a little bit. But maybe if I step this down to, let's say 0.1, right? Then you can see what this does. It will make a vector of each of these plots, right? So obviously if I step this up to 3, there's going to be like 200 of these plots. So I kind of want to make sure I suppress this output. But it'll take a while to run just because it's trying to render 250 of these. But when it does, it'll have it saved. So I'm not going to try see what that is because it'll lag out a little bit. But then you can animate it. So I'm just using list animate. It's another function that I found. Might take a while again, but hopefully it will work out fine after some time. So here you have an animation. So since we've cached all of our animation slides, we can see this is a really nice plot or animation, right? So here you can see the mass kind of moving in the x direction and diffusing out as it levels out over time, right? Which I think is pretty cool. I just like playing with it, right? And you can also export it just using this command here, right? That being said, I understand that was a bit of a tangent, and I'm not sure everyone will find use out of it. But if you want to play with some 3D plots, stuff you can do with it, I think you have all the tools to hopefully do most of what you want to do with Mathematica, right? So with that said, that is everything I have to say. So sorry I missed your message, Nashi, but thank you for joining. And for everyone else, that's all I have to say in terms of this notebook. Again, there's examples if you want to work through them. But yeah, give me or Nick a ping if you have any questions about this workshop, or outside if you want some help from someone a bit more local than Stack Exchange. But yeah, thank you for listening. Hope you learned something. But yeah, that's it from me. I'm just gonna stick around to 4 if anyone has questions, but feel free to head out if you'd like. Again, if you have feedback on anything we can improve, the stuff you found useful, give me a ping. That would be pretty helpful, just in case we want to run this in the future. But yeah, otherwise I'll see you guys later. Otherwise I will hang out in this chat for a little more. But yeah, no worries. Thank you guys for joining. Appreciate that. Thank you. Okay, good shout. I guess I will be a Mathematica person. Okay, sure. So did you mean like more examples on how to plot stuff in 3D? So like more specific examples of like surfaces, stuff like that? Okay, yeah, fair enough. I guess I did cover it, but not really like the extent of what you can do with it. So I mean, it's ended and I think everyone's left. But if I'm not sure if you're a first year student, but I don't know, we could run through some examples now. So for example, when you're trying to look at 3D integrals per se, you can, let's say our first function is the plane x plus y, and the second function is x squared plus y squared. Actually, let's make this 2 minus this, right? And then we can make first plot, second plot, and plot 3D, right? Yeah, okay. Yeah, I'm trying to go through that right now. So, like, yeah, if you have like a region you want to figure out how to construct a triple integral for. So let's say our first one is the first function. X goes from -2 to 2. And this one, oh, why did that not work? This one, did I type it? I did type it. Right, and then show. Yeah, so you can, yeah, I guess opacity, you kind of have to look at it, but you get a little bit of an idea of how it looks in 3 dimensions. So what's on top, what's below, left and right, I guess. But yeah, I will look into that if we're running it next year for how to visualize in 3D a bit more. But one of my favorite uses of ClassPad was the solve function. Yeah. So I did go over solve a little bit. Maybe you just missed it, but okay. Yeah. Yeah, I use solve the exact same way as my ClassPad. I just kind of spam oh wait, oh, you said solve, not simplify, yeah. Yeah, I guess I kind of looked over solve as kind of a generalized desolve. But yeah, solve is something that is in Mathematica. I think you use it the same as desolve. What do you think, Milan? Because I know you were here for like in and out, but what are your thoughts on this if you are listening right now or if you're just in the chat or voice chat? Calm, no worries. Thank you, Nick. Okay, I am going to end the recording there. So for anyone watching on YouTube after, hello, thank you for listening, and I'll see you later.